Okay, so this next section in our book here is about the laws of limits or the rules for limits on how to compute limits algebraically. So I'm going to just run through this in your book, kind of explain what these different rules are saying. And then in a separate video, I'll head over to the board and I'll work out some examples of how to apply these rules. But basically, after this section, you should be able to just compute a limit algebraically using these rules or direct substitution if that applies, and we'll see that in an example. So yeah, you can see my screen here, I hope. This is a screen right out of the textbook. Feel free to copy this down if you want. But I think a lot of these are just they make some intuitive sense. So basically the conditions here for all of these are f and g are just functions that are defined over some interval containing a, everywhere except a, and then assume L and M are real numbers such that the limit of f is equal to L and the limit of g is equal to M. So basically we're saying these two limits of f and g exist, and one of them is equal to L and one of them is equal to M. So basically it's like this. The limit of a sum, that's what this first thing is. Basically the limit of a sum is the sum of the limits. So basically you can take two functions, and you have two functions that you're adding together, and you have a limit of two functions or two things added together. You can bust that up into two separate limits. The limit of the sum is the sum of the limits. The difference law, the limit of a difference is the difference of the limits. Constant multiple law. So basically this is saying is if you have a constant times a function, it's the constant times whatever the limit is. So you can just pull constants outside, and we'll see what that looks like in an example too. The product law, the limit of a product is the product of the limits. Limit of a quotient is the quotient of the limits. And then this one right here, the power law for limits, if you have taking the limit of a function raised to a power, the answer to that is the limit raised to that power. And if you think about maybe where that comes from, if you think about what does it mean to raise a function to a power, that's multiplying that function by itself n times. So what you're really doing there is using the product law n times. And then the square root law for limits, the limit of a radical of a function is the radical of the limit. So those are the limit laws. If you want to copy those down, you can. I'm not ever going to have you recite those necessarily, but I think if you understand how they work, you'll be fine. And again, we'll work out some examples here in a second to show you how these work. So I'm going to stop this video, or pause this video. I think I might be able to pause it and head over to the board and work out some examples. So hold on. Okay, so here we are at the board. Here's an example, our first example that we're going to do, where we compute this limit algebraically using the limit laws. So we got this function here, 3 times the quantity x squared minus 2x. We're taking the limit as x goes to 2. Seems pretty simple. So let's use these limit laws to compute this. Now, I'm going to preface this by telling you up front that this is sort of a lengthy process that we're not going to necessarily go through every time. We're going to see how these laws work in action, and then we'll probably take some shortcuts after we get comfortable. So the first thing I'm going to do is I'm going to see I've got two things being multiplied together here. So I'm going to say, oh, that's the limit of a product, which is the product of the limits. Okay, so simple enough. Okay, so the limit of the product is the product of the limits. So I take the limit as x goes to 2 of 3, limit as x goes to 2 of that quantity there. Now the limit as x goes to 2 of 3, if you think about the function 3, that's just y equals 3, a horizontal line, that limit is 3. So we'll take 3 and multiply by whatever we have over here. Now I've got the limit of a sum or a limit of a difference. So I'm going to say that's the difference of the limits. And so now we're there. And now you can see I have the limit of a function to a power. So that's going to equal the limit of the function x squared. And then I'm going to subtract, oh, and that's the limit of a product there. So I'm going to say that's the product of the limits. Okay. I think that last bit might have gotten cut off there. That says the limit as x goes to 2 of x. And now down here I'm going to say, okay, that's 3 times. Now, what's the limit as x goes to 2 of the function x? Well, think about this. That's y equals x. What happens as x goes to 2? Well, that's a nice continuous function there too. So that's going to be 2, but then it's going to get squared minus, and then I've got the limit as x goes to 2 of 2, which is 2. And the limit as x goes to 2 of x, which is just 2. And so what do we have here? I've got 3 times 4 minus 4, 0. Did I pick one that has 0? I sure did. Ha, that's okay. 3 times 0, which is 0. Okay? So that's the limit. That's the answer to this limit problem. The limit as x goes to 2 of this function is equal to 0. Okay? It just coincidentally chose something off the top of my head that ended up being a root of the function. Now, some of you are looking at this and saying, this is stupid. Like, I could have just plugged 2 in there and gotten 0. Why did I have to go through all that process? And you are exactly right. You are exactly right. You could have plugged in 2 there because this function here that we were talking about, that function is continuous at x equals 2. If you were to think about the graph of that function, it would be continuous at x equals 2. And if you're continuous at x equals 2, then the limit equals the function value. And so that's going to happen. So anytime you're dealing with something that you recognize as a continuous function at the point that you're investigating, you could just plug in. You wouldn't necessarily have to go through all these steps. And these steps are crazy. I mean, but we need to understand that the limit of a sum is the sum of the limits. The limit of a product is the product of the limits. Once we have that kind of in our heads and we know how to manipulate that, we'll be much better off. Okay? Let's do a couple more examples here. Let's see, I'll step out of the way here. Let's see if I can get another color here. Let's see, I got 2x plus 1, so I'm going to say the limit as, I got some paper here, as x goes to -3 of x squared minus 2x plus 1 over x plus 1. Okay? So as we look at that limit problem here, and we say, okay, hey, first thing I'm going to do is I'm going to look at this and I'm going to say, okay, I'm going to -3. That's what I'm interested in. Is this function continuous at -3? If I plug in -3 into this, does it go south? Is there anything weird like 0 over 0 or 1 over 0 or 5 over 0? Is anything happening like that? No. I mean, I can just plug 3 into this and I get, whoops, didn't mean to do that. If I plug in 3 into that, I get -3 squared minus 2 times -3 plus 1 over -3 plus 1. And what happens when I do this arithmetic? I'm going to get 9. That's going to be -6 plus 6, so plus 6 plus 1 over -3 plus 1 is -2. So that's 15, 16 over -2, -8. I think that's the arithmetic there. This is stinky when I don't have you guys checking my arithmetic, with me. I don't have anybody say, hey, doofus, that doesn't work out because you added 6 and 4 and got 12. So hopefully my arithmetic is correct there, but I think it is. So yeah, the answer to this limit is -8. Okay? So let's do another example. Direct substitution, by far the easiest, yeah? I mean, that's just so easy. So, erasing here. I could pause the video while I erase. I might have to start doing that. Okay, try this one. I'll move out of the way here in a second. The limit as x goes to 1 of x squared minus 1 over x minus 1. Okay? So now, let's look at this. I can't just plug in 1 into this because this thing falls apart at 1. If you plug in 1 in the numerator, you get 0. You plug in 1 in the denominator, you get 0. And if you remember the other day, I had a term for that. Indeterminate form, okay? 0 over 0, not good, okay? So we got to do something else here. So what are we going to do with 0 over 0? Well, the first thing we're going to do is, if you notice here, the numerator can factor. I'm going to change colors here, and I'm going to say, okay, well, what if I factor that numerator into x minus 1, x plus 1? Okay, I got that. Seems pretty likely. Pretty nice. And then those two things cancel. In fact, if you remember from your Algebra 2 pre-calculus days, we call this a removable discontinuity. It's a hole in the graph. And then I'm left with the limit as x goes to 1 of x plus 1. And that's now something I can just plug in 1 to and get 2. Okay? So if you were thinking about the graph of this function here, x squared minus 1 over x minus 1, the graph of this function is going to have that removable discontinuity at x equals 1 and the y value would be 2. So at that point, there would be that hole in the graph. Okay? And so, in fact, this function, if you think about what it would look like, is just going to be the line y equals x plus 1, except it's going to have a hole at the point 1, 2. So it would look like this. Okay, and I don't know if you can see that hole there, but yeah, you can see it pretty good. So this is the method of factoring and canceling. Okay, that's how what we call it there. Let's try another one of those real quick. This is probably the most common technique, so we're going to do 2 examples of this just to get you feeling comfortable. Here we go. Ready? The limit as x goes to 2 of x squared minus 5x plus 6 over x minus 2. Okay. Yep, you can see that. Just making sure. So I'm looking at this and I say, okay, can I plug in 2 here? If I plug in 2, this thing's going to fall apart. First of all, the denominator is 0, which is not necessarily a good thing. Although if the denominator were 0 and the numerator weren't 0, this would have a vertical asymptote at x equals 2, so the function would be going or and then so the limit would be infinity or negative infinity. But if you do some quick arithmetic, 4 minus 10 plus 6, that's also 0. So we have 0 over 0 again, which we know as indeterminate. So our method of dealing with this indeterminate form right now is going to be to factor. So let's see, can you factor the numerator there? Well, I hope you can factor that into x minus 3, x minus 2 over x minus 2. Okay? And after you factor that numerator, you say, hey, woohoo! Those don't factor, they cancel, which is basically removing a 1. And now I'm left with the limit as x goes to 2 of x minus 3. And I look at that and say, hey, now I've got the craziness removed. I can just plug in 2 here. And the reason I'm allowed to plug in 2 here is because I'm using those limit laws, and I'm just sort of bypassing all of that. I'm saying, hey, I understand how this works. 2 minus 3 is negative 1. Okay? So the answer to this limit problem is negative 1. Okay? So just here's 2 examples here sitting right next to each other. Both of them were taking the form 0 over 0 when we initially substituted in. But this one was approaching negative 1, and this one is approaching 2. That's why 0 over 0 is what we call indeterminate. Sometimes it's going to approach one thing, and sometimes it's going to approach something else. Okay? Now let's do one more example here for this video. And this one's probably going to be the one that is going to be the most algebraically challenging for you. So I'm going to kind of break it down and maybe go nice and slow for you. I have it written on my paper here so I can cheat. The limit as x goes to 1 of the square root of 5 minus x minus 2. That's 2 is not inside the square root, by the way, over x minus 1. Okay? So can this be done by direct substitution? If I just plug in 1 here, what do I get? 5 minus 1 is 4. Radical 4 is 2. 2 minus 2 is 0. And, 0 over 0. Dang it. Okay. So we're going to have to do something. Well, the last 2 examples, we got 0 over 0, and we just factored. Meh. You can't factor that. Oh, shoot. So what are we going to do? Little algebraic trick here that maybe you have to dig a little bit to remember, but there's a trick called multiplying by the conjugate. You multiply by a clever form of 1, and in this case, it's what we call the conjugate. I look at this radical here in the numerator, and I think, okay, if I multiply that by radical 5 minus x plus 2 over radical 5 minus x plus 2, first of all I'm doing is multiplying this whole expression by 1 because the numerator and the denominator are the same. So this is just multiplying by 1, so I'm not changing the value of anything. And what I've done here is I've got now a difference of squares that's been factored. Radical 5 minus x minus 2, radical 5 minus x plus 2. And so when I multiply those, a plus b, a minus b is a squared minus b squared. So it's going to be radical 5 minus x squared minus 2 squared, which is 4. And then that denominator, I don't even want to think about what that looks like. I'm just going to write it as the big mess that it is. Okay? Now, what is radical 5 minus x squared? Well, it's 5 minus x. So that's what the numerator is going to simplify to, correct? And now we have x minus 1 times that big fat mess. Okay, and then I do some quick arithmetic here, and I say, oh, 5 minus x minus 4 is the same as 1 minus x. Whoops, this radical that 2 got snuck under that radical there, and I didn't mean to. Put parentheses there. Okay. So now, I'm going to use a different color here just to make this pop. 1 minus x and x minus 1. Those two stacked on top of each other are actually equal to negative 1. I'm going to show you how right here. So if I factor out a negative 1 into the numerator, what's negative 1 factored from 1? Negative 1. What's negative 1 factored from x? Plus x. Okay, so there's our new denominator. And now check this out, friends. Negative 1 plus x, x minus 1, those cancel. Okay, and now we're left with, next time I'm going to have to write it a little bit smaller, because I have to go over here. Oh, somebody just texted me who texted me earlier. I think it was Megan texted me earlier and asked me a question about something, and she just texted me back. So thanks for responding. I'm going to go over here, and I'm going to say, okay, this is equal to the limit as x goes to 1 of -1 over the square root of 5 minus x plus 2. Oh, I keep sticking this radical. Ah, I did it again right there. Sorry about that. And now that denominator looks like a hot mess, but it really isn't, because I can plug 1 in here and nothing falls apart. 5 minus 1 is 4. Square root of 4 is 2. 2 plus 2 is 4. So this ends up being -1/4. Okay? So this little conjugate trick, I'm going to have you maybe do 1 or 2 of those just for practice. It's a good algebra skill to have in your back pocket. It'll come up every now and then in a calculus setting. But yeah, so that's it. I'm going to go ahead and write these problems down for you that I want you to try from this section 2.3. And I'll also type these out, but sometimes, if you're taking notes, it's just nice for you to have them here. 2.3, 84, 90, 93, 94, 96, 99, 102, 103, 108, and 111. That looks like a lot more than it really is. A few of those you're just going to be able to do by direct substitution, and only a few, like a couple at the end, are going to be some more algebraically involved. So take a look at those problems, give them a shot, and we'll see you next time.